Hi everyone, I'll be demonstrating here how the DDoS attack affect network performances in SDN network. Before we start, I'm going to show the tools I use to monitor the system. First, I use the system monitor, which is the graphical tool that shows the CPU and memory usage with nice visual graph. Second, I use HTOP, which is the terminal-based tool that displays CPU, memory, and process information in real time with colors. These tools help us see exactly what's happening to the system during our test. Now let's look at the TCP server performance before any attack. I set up the host H1 as the TCP server on port 5001 and ran the test for 10 seconds using JPref. The server achieved very high throughput of 4281 megabytes per second on average. The bandwidth was very stable with only small variation around 500 megabytes per second. The jitter, which measured delay variation, was very low at just 1 millisecond. Most importantly, there was a zero packet loss and the performance stayed consistent throughout the entire test. On the client side, host H2 connect to the server at IP address 10.0.0.1 on port 5001, and also that's on for 10 seconds. Here we can see TCP slow start behavior because this means the bandwidth start low and gradually increase as the TCP adjusts its sending window. The bandwidth grows over the time as the connection learn about the network condition. The peak performance reached 2756 megabytes per second, and this shows TCP is smart and adapt to the network. Let me summarize the TCP performance before the attack. The server bandwidth was approximately 4281 megabytes per second, while the client averaged about 2300 megabytes per second. The CPU usage was very low at only 11.6 across the three cores, and the memory usage was at 82.8%, which is 5.4 out of 6.5 gigabytes. Jitter remaining at about 1 millisecond, and the packet loss was 0%. The bandwidth graph display how TCP starts slowly and how then becomes steady. Now let's look at the UDP performance. I configured host H2 as a UDP client, sending to server at 10.0.0.1 on port 5001 with the target bandwidth of 1 megabyte per second for about 10 seconds. The UDP performance was excellent because the bandwidth was perfectly stable, showing completely flat line on the graph. There was a zero packet loss. All 895 packets arrived successfully, and the jitter was extremely low at only 0.020 millisecond. The actual bandwidth matched the configured rate exactly, and all 896 datagrams were sent successfully. To summarize the UDP before the attack, the bandwidth was constant at 0.125 megabytes per second, shown as a flat line throughout the entire test. Packet loss was 0 out of 895 packets, and jitter was only 0.020 milliseconds. CPU usage was 11.6%, and the memory was 82.8%, which is showing very low overhead. All 896 datagrams were successfully transmitted with no retransmission needed. Because UDP is connectionless with only an 8-byte header, it processes quickly. This makes UDP highly stable and ideal for the real-time traffic in the clean network environment. This is what happened to the TCP server during the attack. The server was listening on port 5001 with reports every 1 second. Looking at the graph, you can see the bandwidth in the upper section with multiple colored lines, approximately 20 different TCP streams. The axis ranged from 0 to 5 megabytes per second. Each colored line represents an independent TCP connection. The through output oscillates widely between 0.2 and 0.9 megabytes per second. The pattern shows repeated peaks and valleys across the connection, across all the connection. No single stream could maintain consistent through output. Some connections briefly achieved higher through output before experiencing a sharp decline, which indicates network congestion and packet loss. The vertical spread of these colored lines shows variable latency between packets, which badly degrades performance. Several threads reported minimal throughput around 0.25 megabytes per second, suggesting outs and connection resets due to the overloaded server. The analysis of TCP result after the attack. The bandwidth collapsed by 99.98% from 4,281 megabytes per second down to just 0.87 megabytes per second on the server. The client dropped 92.7%, going from 2,300 down to 167 megabytes per second. CPU usage shot up 82.7% for all across the course, and the system load increased to 6.58. There was severe fluctuation ranging from 50 to 350 megabytes per second, plus many retransmission. Flood attack exhausted the connection table, causing the timeouts and the failures. Essentially, the TCP stateful processing, which requires maintaining connection information, and become a major bottleneck under the attack. During the attack, the client H2 was trying to connect to the server at 10.0.0.1 on the port 5001 for 10 seconds. The graph shows the speed in megabytes per second, and you can see the speed goes up and down widely between 50 and 350 megabytes per second. And this shows the connection is very unstable, and the average speed was about 167 megabytes per second, which is the 92% lower than before the attack. The sharp up and downs you can see that happen when the connection tries to recover but then timeout and fails again. So this is the UDP performance under the attack. As you can see, it's maintained the configured rate of 0.125 megabytes per second with no throughput dropout at all. And the packet loss increased slightly to 1.1%, which means 10 out of 894 packets were lost. Jitter increased from 0.020 to 0.138 milliseconds, and CPU usage was around 70.2%, which was actually lower than TCP under attack. Because UDP is stateless protocol, it kept sending packets despite the congestion. There was a slight packet loss, but no protocol level failure occurred. This makes UDP more resilient in DDoS scenarios. This is the summary of everything. Before the attack, TCP had bandwidth of 4,281 megabytes per second, which dropped to 0.87 after the attack. UDP maintained 0.125 megabytes per second, both before and after. CPU utilization for TCP went from 11.6% to 82.7%, while UDP went from 11.6 to 70.2%. TCP had a zero packet loss before but high retransmissions after. UDP had zero packet loss before and only 1.1% after. Jitter for TCP was 1 millisecond before and became variable after. And UDP jitter increased from 0.02 to 0.138 millisecond. TCP was excellent and stable before but became very unstable after. UDP had a flat stable performance before with only slight loss after.